Hello, my name is Josh Lamphere and my teammate is Andrew Gunnett. Today we'll be talking about our project, the 3D printed wakesurf core, and how we hope it will challenge the industry standard of foam cores and wakesurf boards. Our project is designed to eliminate the physical labor involved in shaping a wakesurf board core. Typical foam core blanks require an excessive amount of physical processing before the board can be glassed and used. We will present an innovative design and process using 3D printers that will not only produce an easy assembly, but also increase the strength, durability, and customization of the board itself. We have two separate lists of goals for this project. Our team goals are to create a surfable 3D printed board that has the same feel as traditional foam core boards. The next goal is to make these files open source to allow others to manufacture their own boards without the expertise of foam shaping. The second list of goals is centered around the enterprise we are a part of, Boardsport Technologies. As upperclassmen in this enterprise, we hope to further showcase the plausibility of 3D printing in our projects while providing the necessary documentation to reproduce our ideas or to further innovate or improve upon our manufacturing methods. 3D printing allows for complex models, but the problem involves running accurate FEA simulations because of the different infill properties when printed. To account for these differences, two FEA simulations will be ran on the model. The first simulation will be with 100% infill, while the second simulation will be ran with 0% infill. Then, a tensile test with the same physical model and properties will be ran to confirm our FEA results. The experimentation results will help confirm the strength of 3D printed designs with various infill properties because of the stress-strain curves produced. AccuShaper board design software was used to produce the design for our square nose wake surfboard. This allowed the team to export a STL file of the board into Mesh Mixer, which allows for the editing of STL files. Inside of Mesh Mixer, the whole model was split into 10 pieces, as shown in the top GIF. These 10 pieces were then exported as separate STL files to allow for easier manufacturing. After splitting the board into 10 pieces, the files were imported into Ultimate Kira. This software allows for the overall editing of the printing properties of the model and production of G-code for the 3D printing. The bottom GIF shows how the selected pieces look after slicing the model for post-production. After printing these pieces, they will be bonded together by epoxy. After the bonded pieces have hardened, fiberglass and epoxy will be applied with 2 layers on the top side and 3 layers on the bottom. This will seal the board and provide a smooth running surface for surfing. This next slide is about the difficulties and accomplishments that we came across during the process of making a 3D printed surfboard. As noted in the manufacturing steps, AccuShaper was used to create the board design. The problem we had with AccuShaper was it only exported files in an STL format. Some of you may not know, but the STL file formats are not solid bodies and are usually unable to be imported into a CAD platform for editing. This made it difficult to perform FEA on our design and limits our ability to make edits or add design features into the body. With the print volume of the pieces being so large, since it is a 5-foot long board, finding a 3D printer with a large enough print volume and keeping it cost efficient has been hard. Our accomplishments have been finding the software Mesh Mixer, which allows for STL files to be imported and edited. This allowed us to split the board into manufacturable pieces. After successfully printing a test nose piece and fiberglassing said nose piece, the team believes the 3D printed core with the traditional layers of fiberglass applied to the core will be as strong, if not stronger, than foam core boards without the sacrifice of buoyancy or rideability. We successfully printed a half-scale model of the board, then assembled and epoxied the pieces for test of fit and to make sure no revisions were necessary. Finally, we would like to thank our sponsors, the Engineering Manufacturing Initiative and General Motors for accepting our project proposal and granting us funding. Without this funding, our project would still only be on a computer. Also, we would like to thank Dr. M, Professor Cam Haddon, Professor Laviak, and Nick Hendrickson for providing their expertise and professional opinions to make this project move along smoothly.